Welcome to Chapter 2, where we explore Gaussian process modeling. Gaussian processes are the engine that powers Bayesian optimization, providing not just predictions, but also uncertainty estimates. This unique capability of quantifying what we don't know is what enables the intelligent exploration-exploitation balance we discussed in Chapter 1. A Gaussian process is a distribution over functions, completely defined by two components: a mean function and a covariance function, also called a kernel. The key equation shows that any function drawn from a GP is characterized by these two elements. Unlike regular regression, which gives us a single prediction line, a Gaussian process gives us a distribution of possible functions, all consistent with our observed data. This probabilistic view is what allows us to quantify uncertainty. The predictive distribution is where Gaussian processes reveal their power. Given observed data, we can compute both the predicted mean and the predicted variance at any new point. The formulas involve kernel matrices, but the intuition is simple. Predictions near observed data have low uncertainty, while predictions in unexplored regions have high uncertainty. This is visualized as confidence intervals that widen away from data points, directly guiding where Bayesian optimization should explore next. Let's see a practical example with chemical reaction yield data. We have 5 temperature measurements ranging from 50 to 130 degrees Celsius, with yields peaking around 90 degrees. The Gaussian process fits a smooth curve through these points, with the 95% confidence interval shown as the shaded region. Notice how uncertainty increases at the edges, around 40 and 140 degrees, where we have no data. This tells us exactly where additional experiments would be most valuable. The kernel function determines the smoothness and character of our predictions. The RBF, or squared exponential kernel, produces infinitely smooth curves, ideal for temperature-yield relationships. The Matern kernel with nu equal to 1.5 is once differentiable, providing moderate roughness that's robust to noise. Matern with nu equal to 2.5 offers balanced smoothness. The rational quadratic kernel handles multi-scale phenomena by mixing RBF kernels of different length scales. Choosing the right kernel for your data is crucial for accurate modeling. When working with multiple inputs, like temperature and pressure, the RBF kernel naturally extends to higher dimensions. The left plot shows predicted yield as a heat map, with our 5 experimental points marked. The right plot shows prediction uncertainty, which is high in regions far from any data point. An important insight comes from the optimized length scales, about 12 degrees for temperature and 0.68 megapascals for pressure. Because the two are in different units, we compare each against the range it was fitted over, roughly 1/5 of the temperature range versus 1/3 of the pressure range, which means the yield actually varies slightly faster along the temperature axis. Comparing kernels on the same data reveals their different behaviors. RBF produces the smoothest prediction, which might overfit smooth assumptions to noisy data. Matern with nu equal to 1.5 creates rougher predictions that may better capture true variability. Matern with nu equal to 2.5 falls in between. We compare kernels using log marginal likelihood, where higher values indicate better fit. In this example, RBF has the highest likelihood, suggesting the underlying process is indeed very smooth. Gaussian process hyperparameters, including signal variance, length scale, and noise variance, are automatically optimized using maximum likelihood estimation. The log marginal likelihood has 3 interpretable terms: a data fit term, a complexity penalty that prevents overfitting, and a normalization constant. Optimization uses gradient-based methods like LBF-GSB, and we typically run multiple restarts to avoid local optima. Each hyperparameter has physical meaning. Signal variance controls the function's amplitude, length scale determines correlation distance, and noise variance represents measurement error. Validating your Gaussian process model requires checking multiple diagnostics. The predicted versus observed plot should cluster around the diagonal line, with r² above 0.9 for a good model. The residual plot should show a random horizontal scatter, indicating homoscedasticity. The residual histogram should approximate a normal distribution. Most importantly, the uncertainty calibration check verifies that about 95% of observations fall within the 95% confidence interval. In our example, 93.3% coverage indicates well-calibrated uncertainty estimates. Let's summarize our key learnings. Gaussian processes are defined by mean and kernel functions, with RBF for smooth data and matern for robustness. Maximum likelihood estimation automatically optimizes hyperparameters. Uncertainty is quantified as confidence intervals that widen in unexplored regions. Cross-validation and residual analysis validate our models. In Chapter 3, we'll learn about acquisition functions like expected improvement and upper confidence bound that use these uncertainty estimates to intelligently select the next experiment.